Hello, this is Miss McClellan here to go over notes IM2 8.4.3 with you, circles in context. So in previous lessons and classes, you've developed methods to calculate the area and circumference of a circle with radius r. Circumference, c, is equal to 2 pi r, where r is the radius, and the area, a, is equal to pi r squared. During this lesson, we're going to work to solve problems from different contexts involving circles and polygons. And we have two learning goals. We'll write them in the first person. I will be able to 1. Convert back and forth from radians and degrees, period, and 2. Apply what I know about circles and their measurements to story problems. And interpret my solutions within the context of my problems. Let's get started. 8-100. While Earth's orbit, meaning path, around the Sun is a little bit elliptical, it can be approximated by a circle with a radius of 93 million miles. A. How far does Earth travel in one orbit around the Sun? Let's take a look. Here is a circle. It represents the Earth's orbit. Here's a sun. I've got my sun. Here's my Earth. And how far does it travel as it goes around the sun? Well, that's equal to the circumference of this circle. And the radius is 93 million miles. Therefore, my circumference, 2 pi r, is equal to 2 times pi times 93 million miles. If you put that in your calculator, you should get 186 million pi miles, which is approximately 584,336,234 miles. Now we want to know how fast Earth is traveling in its orbit in space. I mean, to calculate miles per hour. We do have enough information to do this, assuming you know that a year is 365 days. So first of all, 1 year equals 365 days. We want this in miles per hour. We know how many miles. We're going 584,336,234 miles. There are 24 hours per day. We can get to hours and miles. Okay, so first of all, we have 584,336,234 miles per year. Multiply that by every year is 365 days. Multiply that by every day is 24 hours. Here, using some unitary analysis, which hopefully you've learned in chemistry, but I'm not sure what science teaches it. Anyway, years cancels, because you've got years divided by years, and days canceled, because you've got days divided by days, and you're left with miles over hours with their numbers. So let's do some multiplication. On top, we have 584,336,234 miles. And that's out of 365 times 24 hours. And if you put that in your calculator, in the end, you will get 66,705. And the units are miles per hour. I forgot to write hour up here. We did it. Okay, next problem. This problem is very similar to a checkpoint problem. A certain car's windshield wiper clears a portion of the windshield in the shape of a sector as shaded in the diagram at right. If the wiper pivots 120 degrees during each swing, what is the area of the windshield that is wiped in each swing? I want to think about this visually. We can get the area of the whole sector by knowing that we have a central angle of 120 degrees and a radius of 20 inches. Notice that I combined these two pieces. Now, in order to know the area of just the part that the windshield touches, I need to take away a little bit of that total. So I need to take away the part of that total which has just the bottom 5 inches, which still has 120 degrees as the central angle. And that will give me just the part I'm interested in. Just this part up here. So recall that the area of a sector is equal to the central angle for the sector divided by 360 degrees. Take that and multiply it by the area of the whole circle, which is pi r squared. Okay, so the area of the whole arc, including the part we want to subtract, is 120 divided by 360 times pi times 20 squared. And I need to subtract this little part, which is, again, 120 divided by 360 times pi r squared. In this case, r is 5. And that is going to equal the number that we want. And if you put this in your calculator, piece by piece, the first one, the first term, you should get 418.6 repeating, and for this next term, you should get 26.1 with the 6 repeating, which gives, again, using your calculator, about 392.7. I'm just going to keep it as 0.7 because I'm rounding, inches squared. So the area of just the part of the windshield that is wiped by the wipers is 392.7 inches squared. 8-102, the cookie cutter. A cookie baker has an automatic mixer that turns out a sheet of dough in the shape of a square, 12 inches wide. His cookie cutter cuts 3-inch diameter circular cookies. So each of the circles are 3 inches in diameter, etc. The supervisor complains that too much dough is being wasted and orders the baker to find out what size cookie would have the least amount of waste. Our task is to analyze this situation and determine how much cookie dough is wasted when a 3-inch cookie is cut. Then we're going to check how much dough would be wasted for a different diameter, and then we'll compare our results. First, we'll do the 3-inch diameter cookies. We have a 12 square inch sheet of dough filled with 3-inch diameter cookies. Since 3 times 4 is 12, we can fit 4 times 4 cookies. So the area of dough taken up by cookies will be 4 times the area of a circle with a radius. Careful, not the radius of 3. The radius is 1.5 of 1.5, period. So I'm going to find the area of a circle with a radius of 1.5. I'm going to multiply that by 16. Oops, I made a mistake. The area taken up by cookies will not be 4 times the area of a circle with a radius of 1.5. It will be 16 times the area of a circle with radius 1.5. Equals pi times 1.5. And that is 100, and the area taken up by the dough before any cookies are cut is inches squared, which is 144 inches squared. So the amount wasted is equal to 144 inches squared minus 112 inches squared, and that equals 32 inches squared. Okay, let's check cookies with a diameter of something easy. Okay, the easiest area to find for a circle is when the radius is 1. And if the radius is 1, the diameter is 2. So I'm going to be checking 2-inch diameter cookies. And because the diameter is 2, and my sheet is a 12 by 12, I will have 36 cookies. So that's because 2 times 6 is 12. So first, again, I'm going to find the area of just the cookies. Area of a single cookie is equal to pi r squared. Here r is 1, not 2. Be careful. 2 is the diameter. So pi times 1 squared, which is just pi. And I need to multiply that by 36 because I'm making 36 cookies. So 36 pi, which is approximately 36 times 3.14, 113. The area of the cookie sheet is, again, 144 inches squared. And that means that in terms of waste, I have 144 inches squared minus 113 inches squared, which is 31 inches squared. That's very close to the last one. And what I'm wondering is if I made a calculation error, because since they're so close, I wonder if they're supposed to be the same. So I'm going to double check my 3-inch diameter calculations. What is this? So I'm going to do the 3.14, I'm doing this part, times 1.5 squared. And that's 7.065, and I treated that as just 7.0. Let me multiply that by 16. 113. Students, look, this should have been 113, which would have made this 31. Wow. Okay. Let's write a short note to our supervisor explaining our results. These are surprising results, and I hope the supervisor trusts our math, because we're right. Turns out that the diameter of the cookie the amount of waste will always be the same. And I think in order to say that, though, we have to make the assuming we use full cookies. Just going to watch that corresponds to an arc length equal to the radius. The radius wraps around the circle about 6.28 times pi. Here it's gone around pi times. Here it's gone around 2 pi times. With that GIF in mind, the radian measure of a 45-degree central angle of a circle with a radius 5. Let's draw that circle. Radius is 5. The angle is 45 degrees. Now, pi radius is around the circle, so this should equal 180 degrees. Since these things are equal, I'm going to divide one side by the other to get a measure of a unit. 180 degrees. I'm going to take this special 1, because this equals 1 conceptually, and multiply it by 45 degrees. And doing that cancels the degrees and leaves me with just a portion of pi. This is pi times 0.25. Usually we write things in terms of pi as fractions, and 0.25 is equal to 1/4. So this is 1/4 of pi, which we would usually write as pi over 4 radians. Meaning the radius 5 would make it pi over 4, so about 75% of 5 would be the sector length. The arc length. Next, what is the radian measure of a 45-degree central angle of a circle with a radius of 1? Okay. So the radius is 1. I'm again going 45 degrees. And look, I think it's going to be the same because we're talking about how much of the circle is covered by this many radians. But I want that to have some feeling for you. So I'm going to show you with a little demonstration. Here we have a circle with a radius of 1, just like our problem. Now, if I haven't moved at all, I've gone 0 radiuses. If I move this far, then I've gone about 1 radius. If I move this far, I've gone 2 radiuses. And that just means that it's asking about 45 degrees. Well, 45 degrees is halfway to 90. So it'd be probably about here. But let's check with arithmetic. All right. So we're going to use the same method as before. Pi radians over 180 degrees multiplied by 45 degrees. Look, the actual radius of 1 doesn't even come up. So of course it's the same. This is actually the same equation. This is again pi over 4. That's the number of radians. Okay, we continue. Consider if the central angle of a circle has a radian measure of pi over 3. What is the angle of its measure, this time in degrees? Okay. angle, radian measure of pi over 3. Now, before I used pi over 180 as my multiplier to convert from degrees to radians. This will take us from degrees to radians. Similarly, 180 over pi will take us from radians to degrees. So we have pi over 3, and we're going to multiply that by 180 over pi, which is 180 over 3, which is 60 degrees. And that's what we thought it should be, because we were about a third of the way to pi. Next, the radian measure of a 90-degree angle is pi over 2. What must the radian measure of 180 degrees be? Well, we've actually been using this piece of information. 180 degrees equals pi. Because the whole way around a circle is 2 pi. 180 degrees is halfway to 360. And similarly, pi is halfway to 2 pi. We have a little summary. What is a radian? Now, a radian is a unit of measure for angles. It is based on the angle that is required to create an arc length of 1 radian. 180 degrees is pi radians. Use that fact and we can convert back between degrees and radians. So for example, if we want to convert 30 degrees to radians, we would do pi divided by 180 divided by 30 degrees equals 30 over 180, which is 1/6 times pi. We write these as fractions. So we would write this as pi over 6. Second example, convert 3 pi over 4 radians to degrees. So we have 380 degrees over pi, and we get 3 times 180 divided by 4. And if you put that in your calculator, you get so here would be pi over 4, 2 pi over 4, 3 pi That's it. That's the end of the note. I hope you have a great day, and I'll see you next time. Bye, everybody.